All right, in this video, I'm going to be working through 2021 BC number 4. This is the graph of the derivative problem. So they're saying let f be a continuous function defined on the closed interval -4 to 6, and they're showing it to you, and it's the piecewise linear function. So g of x is an antiderivative for f. It's the integral from 0 to x of f of t dt. All right, so it's the type of area counting function where we're going to start at 0. On what open intervals is the graph of g concave up? Give a reason for my answer. Okay, I can do that. So what I'm going to do is I'm going to say, first of all, in order to find the concavity of g, I need its second derivative, right? I'm not looking at the graph of g or g prime or g double prime. Well, maybe I am. But I don't know that yet. So g prime of x equal to f of x. Second fundamental theorem of calculus. Therefore, g double prime of x is going to be f prime of x. Okay. So, if I'm looking for a sign change in g's second derivative, I'm looking for just as the same as a sign change in f's first derivative. Well, that would be like, pardon me, I'm not looking for a point of inflection. I'm not looking for a sign change in g double prime. I just want to know where g double prime is positive. Okay, so I would say g is concave up when g double prime of x, which is f prime of x, is greater than 0. Okay. And that happens, okay, where's the slope of f positive? That's from -4 to -2. And also here, that's from 2 to 6. All right, next we have ourselves a product rule situation. So we are going to have, okay, p of x is g of x times f of x. Find p prime of 3. So what we're going to need to do is find p prime of x, and then we'll plug in 3, and it should go pretty well. So p prime of x, I'm going to have to use the product rule. So I'm going to take the derivative of one of them while leaving the other the same. Then I'm going to add in, leaving the first one the same, taking the derivative of the other one. But since I know already that g prime of x is equal to f of x, I might just say, you don't have to do that, but I might just say f of x squared plus g of x f prime of x. Okay. So that p prime of 3 is equal to f of 3 is, what is it, -3? Okay, -3 to the 2 power plus g of 3, that's going to take some work here. Okay, so I'm going to just hold on to that for a second. And f prime of 3 is equal to 1. Okay. So I need to do a little additional work to figure out what is g of 3. I don't remember doing this when I worked this problem earlier, but I'm sure I did. Okay, got to find g of 3. Well, g of 3 is going to be equal to the integral from 0 to 3 of f, which is going to be, oh, this one's not so bad because this triangle here and that triangle there cancel each other out. And so I'll have -3.5. All right, so that's -3.5. I mean, that's 5.5, or you could just leave it like that, and that would be just as good, right? All right, part C looks like it's going to be a Lhopital Rule question, but after last year, we learned that not all limits in AP Calculus require the use of L'Hopital's rule. So what we're going to do is we're going to definitely need to check to make sure that as x approaches 2, g of x and x squared minus 2x are both going to 0. Now, I can see that x squared minus 2x is definitely going to 0. G of x, it's definitely going to 0 because of that balanced areas thing that I was talking about in the previous part of the problem. All right, so I'm going to say that x approaches 2 of g of x over x squared minus 2x is going to, I mean, if you wanted to be really fancy, you could say this is half of 4 is 2 minus 2, you know, for the areas. Over 4 minus 4. The important thing is that you're not saying this is equal to 0 over 0. Don't be saying that, right? Okay, so since it's going to 0 over 0, we're going to use Lhopital's rule. Okay, and since the derivative of g is f of x, this is equal to now the limit as x approaches 2 of g prime of x, which is f of x, divided by 2x minus 2. Okay. Then we're going to plug back in on it, and I'm going to get, as x approaches 2, f of x is approaching negative 4. Over 2x minus 2 would be 4 minus 2 is 2. And that's going to be where I stop. Okay? That's definitely one that we can do, provided that we know our second fundamental theorem. Now the last problem we've got is find the average rate of change of g on negative 4 to 2. I'm just going to start by doing that. All right, so average rate of change is going to be g of 2 minus g of negative 4 over 2 minus negative 4. Okay? That's just definition of average rate of change. It's rise over run. So I need to figure out what is g of, I've already did g of 2, I think. Yeah, I did that when I was doing the limit problem. That's 0. G of negative 4, not really sure what that's going to be, but I can figure it out. I'm pretty certain. What I'm going to do is I'm going to say, g of negative 4 equals the integral from 0 to negative 4 of f, which is the opposite of the integral from negative 4 to 0 of f. So that's probably what I'm going to do. I'm just going to count it forwards and then make it negative at the end, is what I'm saying here. Okay, so this one, all right. There's all sorts of ways you can count this area. What I'm going to do, though, is I'm going to make this a triangle, that another triangle, and then this a rectangle. Okay, so this has got 8. I can count those. This is going to have an area of 6, because 1/2 times 2 times 6 is 6. Yes.
Why would you put a negative sign in front of that interval?
Oh, because from 0 to negative 4 is backwards, so I want to go forwards and then just make it negative at the end. It's kind of what I'm saying here. Yeah. Because I know that oftentimes people in my class are very good at being like, okay, I'm going to start backwards so above the axis is negative and below is positive, and I know when I'm about to get confused, and that is right when I feel like I'm about to get confused, so I just avoid it. All right, so that's 6, that's 8, and this is 2. And so this is going to be 16. So it would be the negative of 16. Right? Now I think I'm pretty much ready. Yeah, I can do the average rate of change because I already said that g of 2 equals 0. So my average rate of change there is equal to 0 minus negative 16. Over 2 minus negative 4. That's my average rate of change. Okay. And does the mean value theorem guarantee a value of c between negative 4 and 2 for which g prime of c is equal to this average rate of change? Justify my answer. Well, I think what I need to do is remind you of the statement of the mean value theorem. And so I'm just going to pull that in real quickly right here. And it says that if a function f is differentiable on an open interval, really it needs to be continuous on the closed interval that corresponds, then there is an x value, x naught, that's between a and b, for which f prime of x naught, I was supposed to have an x naught there, yep, is equal to the average rate of change of f on the interval a to b, which is rise over run. Okay? So if the function is differentiable, then the mean value theorem guarantees the existence of a place where the instantaneous rate of change equals the average rate of change. Let's go back here. What do they want you to say? Here. Enjoy that. What do they want you to say? They want you to say, oh, hey, look, this graph is not differentiable, so the mean value theorem doesn't apply. That is not what is the right answer, though, right? What we need to think about is, what are they actually asking us about? They're asking us about G. Is G differentiable? Yeah, and it is. Okay, so I'm just going to kind of scoot this up a little bit so I have some room to write. So G is differentiable on, let's say, -4 to 2. Because G prime equals F, and F exists everywhere, and F exists on that interval. This is very detailed.
Did you say F is continuous?
Yes, F's continuity. Did we have this discussion yesterday? I feel like I had this exact same conversation with somebody yesterday, but they were asking about the continuity of F, and yes, that's good enough. The continuity of F is actually more than what this would require, I think. But if a function is continuous, it's because it's existing, right? It can't be continuous somewhere it doesn't even exist. So if you say it's continuous on that whole interval, that means F exists everywhere. G's derivative exists means it's differentiable, and we can apply the mean value theorem. So, and F exists on -4 to 2. So the mean value theorem does guarantee such a, what did it say? Such a value. Guarantees a value. And maybe just to catch the reader's eye, I'll just underline does. Such a value. Okay. And that's number 4. I thought this one was like very manageable for us.